All right, welcome Ralston Valley High School chemistry students. You are about to watch a lecture discussing a continuation of our investigations into the world of quantum mechanics and modern atomic theory. This is Chapter 7, Lecture Number 2, the Wave Mechanical Model. So let's begin. So where we left off after our last lecture was with a discussion of the Bohr model atom, in which we had those electrons orbiting around the outside of the nucleus at particular energy levels. But there was some difficulties involving that Bohr model atom. Primarily, as soon as we came up with the Bohr model atom, we knew that it couldn't be right. Primarily because an atom which followed a Bohr model would be inherently unstable. If you recall from back in your physics days, we remember that an electron itself is a charged particle, and not only that, it's a moving charged particle. And you also might recall that moving charged particles generate magnetic fields. Now, considering a Bohr model electron, if it's really following a circular orbit the way that it's traditionally diagrammed, that circular orbit implies that the electron is turning and therefore accelerating. It should be experiencing centripetal acceleration. And accelerating charged particles should, based upon our traditional understanding of physics, produce radiation. And that radiation would carry away with it energy, meaning that the electron itself would be losing energy, and that really implies the electron would be plummeting inwards towards the nucleus, which we all know doesn't happen because that would imply basically every single atom would be inherently unstable, and electrons in those atoms should plunge into the nucleus. Now, obviously, we don't observe that happening in the real world, so we knew the Bohr model must not be a complete model of what's really going on inside of an atom. So the replacement for that Bohr model came soon after by what we refer to as the wave mechanical model, or the quantum mechanical model of the atom. The quantum mechanical model of the atom differs greatly from the Bohr model in that whereas the Bohr model was kind of based upon our traditional planetary understanding of an atom, with the electrons taking the place of the planets orbiting around the outside of a nucleus where the sun would be in a planetary model, the Schrödinger model of the atom approaches it from a mathematical standpoint. And one of the strange things about that wave mechanical model of the atom is that it doesn't really tell you where the electrons are so much as the probability of where they're likely to be. It's based upon some scary looking math that if you do some more chemistry or physics in college, you will come across, referred to as the Schrödinger equation. The Schrödinger equation is a mathematical model for an atom that essentially relates the energy of the electron to the potential particle locations. And rather than yielding definitive answers about where that electron really is, it instead gives a range of probabilities about where that electron is likely to be found. Now, if this all sounds very nebulous, that is to be expected given some words that you have familiarity with in terms of electron behavior. In particular, you've previously heard those electrons' positions referred to as in the electron cloud, a very nebulous or uncertain location for them to be found. And the solutions to the Schrödinger equation yield probability distributions that we refer to as electron orbitals. You'll see here on this slide, there is a diagram of what's referred to as an s orbital. That s orbital is not a picture of one electron, but instead a representation of where that electron is likely to be found. Regions where it is darker represent regions where the probability of finding the electron are higher. In particular, note the high probability of finding an electron around the nucleus of this atom at the center. And then we also have regions in space where the electron density is lower, represented by lighter portions of this diagram plot. And if you kind of look at it, this looks very similar to, not surprisingly, something you've seen from your physics days, and that is a point source wave, where we have a series of alternating antinodes where the probability of finding an electron is very high, and nodes where there's essentially zero probability of finding those electrons. So again, we see here a correlation between atomic behavior and wave behavior that was pointed to by our earlier discussions in quantum mechanics. So let's go ahead now and investigate some more of those shapes of these regions in space we expect to find these electrons, these electron orbitals. So depending upon the energy of the electron, we see changes to the shape of the wave. If you think back to your Waves on a String lab from physics, you remember that when we inputted small amounts of energy into the system, that is, we shook the string with not a lot of vigor, we were able to form a standing wave in which there were two nodes on either side of the string and one antinode in the center, and we referred to that as the fundamental frequency. But if we increased the rate at which we were shaking the string, that is, we inputted more energy into the system, we could cause the standing wave shape to change. And by inputting more energy, we were able to form another node along the center of the string, in which point we had two antinodes and a higher frequency wave. And we could continue to do that to higher and higher frequencies, producing more and more and more nodes and antinodes, changing the shape of the wave function. The same sort of thing kind of happens analogously in electron behavior. And it's important to note that just like for the waves on a string, there are only certain allowed permitted frequencies or energy levels of an electron that allow for the formation of a stable standing wave in the atom. Just like for the waves on a string, only certain allowed frequencies of vibration would form a standing wave on that string. That is to say, the energy levels of an electron, and therefore the frequencies of that electron, are quantized values. So let's go ahead and have a look at the shapes of the orbitals derived from the Schrödinger wave equation. When we start off with the lowest energy electron, we see a type of orbital which we refer to traditionally as an s orbital. And that s orbital takes the shape of a sphere. Now, one of the things you might remember from last year is that, again, depending upon the orientation in space of those orbitals, we could have several different what we refer to as suborbitals. But this is a sphere we're dealing with, and no matter which way you rotate a sphere, it always looks the same. So there's really only one suborbital of the s orbital. And again, remembering back to last year, we recall that each of those suborbitals could hold a total of 2 electrons. So with one suborbital, our spherical s orbital can hold a total of 2 electrons. Moving on from s orbitals, we can now move to a higher energy orbital, which is referred to as a p orbital. And that p orbital takes on the shape of a dumbbell. Now again, this is not an electron shaped like a dumbbell. It's that the region in space where we are likely to find an electron based upon the probability distribution described by the solution to the Schrödinger wave function equation at that energy yields a region in space shaped like a three-dimensional dumbbell. Now those dumbbells can be oriented along the x, y, or z axes, which gives us a total of 3 different suborbitals, one along each of those axes. And again, each suborbital holds 2 electrons, which means a p orbital at a given energy level can hold a total of 6 electrons. And just like those standing waves on a string, at higher and higher frequencies, we see more and more complicated wave shapes. Moving along past the p orbital, we next come to what we refer to as a d orbital. Those d orbitals shapes take on, for 4 of the suborbitals, shapes of 4-leaf clovers. And one of them is shaped kind of like we call it a dumbbell with a donut around its waist. And you'll kind of note a pattern here now with 4 4-leaf clovers and 1 dumbbell with a donut. That's a total of 5 suborbitals. You see that the number of suborbitals in each given orbital shape type are increasing by 2 each time, which means we can hold a total of 10 electrons within one of these d orbitals. And moving on next, we can again increase our energy input and then again increase the frequency of our standing wave. We now move to what we refer to as an f orbital. The f orbitals are shaped, four of them, like 8-leaf clovers, if you can kind of imagine a three-dimensional 8-leaf clover. And three of them are shaped like dumbbells with two donuts around their waist. We call them dumbbells with double donuts. The number of suborbitals, therefore, following the same pattern of increasing by 2 each time, now up to 7, which means we can hold a total of 14 electrons within one of these f orbitals. Now, this is not the only types of orbitals that exist out there, just like there's no upper limit to the frequency at which you can vibrate waves along a string. We can also increase energy levels and produce higher energy orbitals. We can move on to like a g orbital, say. It's just that no atom in its ground state, that is in its lowest potential energy state, has any of these higher energy orbitals occupied. So with Schrodinger's wave mechanical model of the atom, we find ourselves in a more confusing position than we had been previously with Bohr's model. Bohr's model looked very much like a planetary system. That was a familiar system to physicists, a system in which you could make careful measurements of things like the positions and momentums of the planets and use them to predict the future state of a system. Now, physicists had been wildly successful for hundreds of years in utilizing this sort of calculation, in particular with planetary motion, because we've all seen that we can, to a high degree of accuracy, calculate the relative positions of the planets and their momentums that allows us to make calculations of the positions of the planets in the future, even doing things like predicting eclipses hundreds and hundreds of years before they actually occur. So this is something that physicists are very, very used to and had kind of got the idea that if we could just get better at measuring positions and momentums of particles in the atom, that the same sort of thing would allow us to understand their behavior. The probability distributions described by the wave mechanical model of the atom seem much more nebulous. But that's nothing compared to what we're going to discuss next here, which is what's referred to as the Heisenberg uncertainty principle from 1927. The uncertainty principle essentially upended the long-term goal of hundreds and hundreds of years of physicists to be able to more carefully measure positions and momentums of objects and use them to make those predictions of the future state of the system. What Heisenberg did was he essentially came along and said, well, as it turns out, no matter how carefully you measure some properties, there's a certain fundamental upper limit to the degree of certainty or precision that you can know some measurements. Essentially what he says is, well, good luck trying to measure things more carefully to get a better understanding of a system, because in some instances there are pairs of measurements that are mutually unmeasurable to a higher degree of precision at the same time. And to give you an example of this sort of idea, I want to think a little bit about maybe photography. Something you might have noticed if you've done any photography in the past is that if you're trying to take a picture of a moving object when it's not very bright outside, your photos often come out kind of blurry. So imagine for a moment here that you're taking a picture of a soccer ball flying through the air. And you want to do what the classical physicists did, which was to measure both the position and the momentum of that soccer ball and use it to calculate where that soccer ball is going to be in the future. And so you get out your camera to take some pictures in order to help you with your measurements. If you want to take a picture of the soccer ball to know exactly where it is, you want to make sure that your exposure time when you take the picture is very, very, very small, because the longer that camera is exposing the image, the more motion is going to occur during the time you're taking the image, and the more blurred the soccer ball is going to look. So if you're trying to get a very, very precise measurement of the position of the soccer ball, you want your shutter speed to be as fast as absolutely possible. But as it turns out, if you measure that position of the soccer ball to a high degree of accuracy, when your picture comes out with the soccer ball not really blurred at all, because there's no blur in the image, you don't really know where that soccer ball is actually going. So if you wanted to figure out where the soccer ball was going, you would be better served by leaving the shutter open for longer to record a longer picture, which would give you kind of a general blurring of the image in terms of the motion of the soccer ball, which would allow you to determine how fast the soccer ball is actually moving and in what direction. So on the one hand, you can accurately measure the position with a short shutter speed, but on the other hand, to know where that soccer ball is going, you'd have to use a longer shutter speed, which means that to measure both the position and the momentum of the soccer ball at the same time, you would have a problem in that those two values, position and momentum, are mutually unknowable to a high degree of precision. And this is an example of what we refer to as the Heisenberg uncertainty principle. It essentially tells us that there's a fundamental upper limit to the degree of certainty to which certain pairs of properties can be measured. One big example, as we just discussed, is position and momentum. And more so, the more accurately you measure one of the properties, fundamentally, the less accurately you must know the other. And the math behind that Heisenberg uncertainty principle is described here in the equation shown. The value of delta x here represents the uncertainty in your measurement of position of an object. And the delta mv represents your uncertainty in the momentum of the particle. And essentially what this tells us here is that the product of the uncertainty of the position times the uncertainty in the momentum for that particle, that product is greater than some fundamental limit, which is Planck's constant h divided by 4 pi, which is essentially itself a constant. Now you see here in this equation, there's fundamentally an inverse relationship in those uncertainties. That is, the less uncertainty you find in your position calculation, the more uncertainty there must be in your momentum of the particle in order for the product of position's uncertainty times momentum's uncertainty to be greater than that fundamental limit of h over 4 pi. So now that we have a conceptual understanding of the Heisenberg uncertainty principle, let's go ahead and put it to the test with some calculations. The first example problem we're going to go ahead and do here is to calculate the uncertainty in position of a baseball with a mass of 145 grams that has an uncertainty in the measurement of its velocity of 0.10 meters per second. So we'll start off again with the equation for Heisenberg's uncertainty principle, that is delta x, the uncertainty in position, times delta mv, which is the uncertainty in momentum, being greater than or equal to Planck's constant h divided by 4 pi. And we recognize here that we've given you essentially a mass that we have measured of 145 grams. So really, if the mass is known, really the uncertainty here lies in the uncertainty in our velocity. And we're going to go ahead and rearrange our equation here to solve for the uncertainty in position here by simply dividing both sides of the equation by that uncertainty in velocity, which yields the new equation of delta x equals h over 4 pi times the mass times the uncertainty in the velocity. And we'll go ahead now and plug in our numbers here. We've got Planck's constant of 6.626 times 10 to the negative 34th joule seconds divided by 4 pi times the mass. I'm going to go ahead and put the mass in kilograms here for reasons you'll see momentarily in terms of canceling, because recall that a joule is a kilogram meter squared per second squared. So I'm going to want to have those kilograms cancel out, times our uncertainty in velocity of 0.10 meters per second. And we'll go ahead and do a quick calculation here and cancel out our units, and you'll see that we end up with an uncertainty in our position of 3.6 times 10 to the negative 33rd meters. An incredibly tiny number, so tiny that it seems at this point that does this equation even matter? Yeah, I can measure the position of a baseball to a very high degree of accuracy. But remember, a baseball is a macroscopic scale-sized object with a large mass, and in this case, velocity that was measured to a small degree of precision. But let's take a look now at what would happen if we did the same sort of calculation, this time involving particles within the atom. For example, number 2, we're going to go ahead and calculate the uncertainty in, this time, the velocity of an electron. Again, electron's mass is 9.11 times 10 to the negative 31st kilograms. And that electron is going to be confined within the boundaries of a hydrogen atom. And again, the diameter of a hydrogen atom is approximately 1 angstrom there, about 1.0 times 10 to the negative 10th meters. So if I know that that electron is inside the hydrogen atom, that essentially means that I can know its position to somewhere within that atom. So that diameter of that atom essentially at this point becomes my uncertainty in the position of that particle. So we'll go ahead and do the same sort of calculation, this time rearranging slightly differently here. My Heisenberg's uncertainty principle calculation of delta x times delta mv greater than or equal to h over 4 pi. I'll do a quick rearrangement this time, solving for the uncertainty in velocity of my particle, which gives me a value greater than or equal to Planck's constant h divided by 4 pi times the uncertainty in position times the mass of the particle. And plugging in my numbers here, again, Planck's constant of 6.626 times 10 to the negative 34th joule seconds divided by 4 pi times my uncertainty in position. Again, I know it's somewhere in the atom, so I'll put in that number of 1.0 times 10 to the negative 10th meters for that position measurement, times that mass of the electron of 9.11 times 10 to the negative 31st kilograms. And you'll notice here this time when I make my calculation that the uncertainty and velocity of that electron is now 5.8 times 10 to the 5th meters per second. So that's not a good measurement of certainty. I mean, if I only know the velocity to plus or minus, around at this point now, something in the hundreds of thousands of meters per second, I essentially have no idea how fast this electron is actually going. All I know is that it's somewhere inside the atom. And really, if you think about it, I've confined its position to somewhere inside the atom, but I really don't know where within the atom it actually is. So I don't even know, on an atomic scale sense, the position of the electron itself to a high degree of certainty either. So you can see here how for atomic scale systems where the masses of the particles are very, very small, the Heisenberg uncertainty principle really tells me that treating atoms as deterministic systems where I can make more and more careful measurements to predict their state in the future is pretty much a futile endeavor. And that's what Heisenberg's uncertainty principle really tells us about atoms. So now that we've talked both about the Schrödinger wave function equation and the Heisenberg uncertainty principle, let's go ahead and take a moment to review some of the variables which come about as solutions to that Schrödinger wave function equation. Recall that only specific allowed energy levels are permitted for those electrons. That correlates to only specific allowed solutions to the equation in terms of the variables which we refer to as these quantum numbers. So when solving that equation, we get some numerical values, and those numerical values describe the state of an electron within an atom based upon its total energy level. But again, these are quantized values, which means only specific allowed values will produce a real solution to the Schrödinger wave function equation and therefore a stable orbital. So to begin with, we're going to go ahead and look at the most familiar of these quantum numbers. That's familiar from your Bohr model atom. It's what we refer to as the principal quantum number. That principal quantum number, essentially from a Bohr model atom, correlates to the shell number of electrons that we are dealing with. We abbreviate the principal quantum number with the symbol n, And if you think about the shells of a Bohr model atom, those shells start obviously with the one closest to the nucleus being the first shell and then go up, increasing in number. But there's really no upper limit to the number of shells which can exist. Within a Bohr model atom of an element in its lowest potential energy state, for elements that exist in our universe, there's only 7 total shells that are occupied. But just like books on a bookshelf, just because a book doesn't occupy a shelf doesn't mean the shelf isn't there. So there are higher principal quantum number energy levels that we could see when we excite electrons up to those higher energy levels that just don't exist for any known atom in its ground state. So those values, again, would be allowed between 1 and infinity. Moving on. Our next quantum number is what we refer to as the azimuthal quantum number, or the shape quantum number. This describes essentially the shape of the orbital, those sp, d, and f orbitals. And we use the symbol L to symbolize the azimuthal quantum number. And the values of those range between 0 for an s orbital up to a highest possible value of n minus 1, where n represents the principal quantum number. So for an s orbital, the azimuthal quantum number is 0. For a p orbital, it's 1. For a d, it's 2. For an f, it's 3, and so on and so forth. And if you think back to your periodic table and the structure of that periodic table, we remember that the first energy level, that is when the principal quantum number n is 1, the only orbital present in that first shell is an s orbital, which means that the allowed value there is 1 less than the principal quantum number. So if you have a principal quantum number of 2, that is, you're in the second period on the periodic table, we would see both s and p orbitals, giving us azimuthal shape quantum numbers of either 0 or 1 in that energy level. So generalizing that, we see that essentially the allowed values for the shape quantum number, the azimuthal quantum number, stretch between 0 up to a highest number of n minus 1, where n is the principal quantum number. And continuing along next, we have the magnetic quantum number. That magnetic quantum number essentially describes the orientation in space of the particular suborbital you're dealing with. We abbreviate that magnetic quantum number with the symbol m sub L. And again, thinking back to the shapes of those orbitals within from the Schrödinger equation, you guys might recall that for an s orbital, we said there was really only one allowed orientation in space of the s orbital because it was a sphere and doesn't look different if you rotate it. So for an s orbital, there's only one possible allowed value of the magnetic quantum number, which turns out to be a 0. For a p orbital, we could orient that p orbital along the x, y, or z axes, and that gives us 3 different allowed values of the magnetic quantum number, which, when you solve the Schrödinger equation, give values of -1, 0, or +1. And if you take a look here, you can see then that these values of the magnetic quantum number correlate to the value of the shape quantum number. That is, the values range between -L up to a value of +L, whole number integers between those two values, where L again is the value of the shape quantum number, the azimuthal quantum number. So, last but not least, there's one final quantum number here, which is confusingly referred to as the spin quantum number. That spin quantum number kind of got its name from when we were treating these electrons as if they were just spinning particles in orbits around the nucleus. And it really more relates to the orientation of that electron's magnetic field due to the angular momentum of that electron. Again, an electron is a moving charged particle, and even though it's not really in a stable circular orbit, it does generate a magnetic field due to that rotational motion, or the appearance of its rotational motion. And that's what we refer to again as spin. You probably remember those spin up and spin down electrons from doing our electron configurations last year. So spin quantum number gets the symbol S, and the allowed values of that spin quantum number when you solve the Schrodinger wave function equation always come out as either -1/2 for spin up or +1/2 for spin down. So we've now had a look and seen that you can describe the state of an electron by its quantum numbers derived from the solutions to the Schrodinger wave function equation. And as it turns out, within a particular atom, no two electrons in that atom can share the same set of 4 unique quantum numbers. Essentially, that means each electron has kind of what you can imagine as its own unique address in the atom. And that's what we refer to as the Pauli exclusion principle. It makes a lot of sense that that would be the case, because if you think about it, those 4 quantum numbers really describe where that electron is. And if it shared the exact same set of 4 quantum numbers with another electron, that would essentially mean that those wave functions were superimposed on top of one another, which would, because these are negatively charged particles, relate to the highest possible potential energy state of those 2 particular electrons. So each individual electron gets its own unique set of 4 quantum numbers. Now, seeing that each of those electrons has its own position, what we're going to move to next now is what we refer to as an electron configuration that I'm sure you all know and love from back in last year's introductory chemistry class. These electron configurations essentially describe where all of those electrons are found in which orbitals for a particular atom. And it follows a couple of different processes in order to find the lowest potential energy configuration for the electrons. The first of those processes is what's referred to as the Aufbau process, which is a German term, literally, which means to build up. And so what the Aufbau process really tells us is that electrons will occupy the lowest energy orbitals first before occupying higher energy levels as you add more and more electrons to the atom. And this is a really kind of familiar process with how the world works. If you can imagine taking a pile of bricks, if you dumped that pile of bricks onto the ground, the first bricks to occupy the pile are going to occupy the bottom of the pile. That's the lowest potential energy state, not the top of the pile. That is, the pile of bricks fills from the bottom up, from the ground up, not from the top down. So that's again what we refer to as the Aufbau process. It essentially tells us electrons find the lowest energy state. The other guiding principle for describing an electron configuration is what we refer to as Hund's rule. Hund's rule we introduced to you last year as the bus rule, which essentially tells us that electrons in the same subshell will always occupy an empty orbital before they pair up with a partner. And when they do pair up with those partners, they always pair such that one is spin up and the other is spin down in order to not violate the Pauli exclusion principle. It's the same sort of idea about getting onto a bus. If you get onto a city bus and there's lots and lots of empty seats, you're always going to take your own empty seat before pairing off with a partner, because that would just make things awkward between the two of you. Same sort of idea for electrons. And when we draw these electron configurations up, what we're most interested in is going to be the electrons which are found in the highest principal energy level. Those are the electrons which are found furthest from the nucleus on average. Those are what we refer to as the valence electrons. We're interested in these electrons because, again, they're furthest from the nucleus on average, which means they're most likely to be involved in the formation of chemical bonds. And when counting up those valence electrons, recall we're not talking about the electrons in the highest energy orbital. We're talking about the electrons which are on average furthest from the nucleus, that is the electrons that are in the highest principal energy level, n. So if you have both s and p orbital electrons in the highest energy state, to count the valence electrons, you'd have to account for both those s and p orbital electrons. Note for a moment here, though, that when you're counting those valence electrons, the valence electrons are always in the s and p orbitals, not in the d or f orbitals. Because if you remember from last year when doing these electron configurations, when we fill up those d and f orbitals, they fill the n-1 for the d orbital electrons and the n-2 for the f orbital electrons energy levels, which means they're essentially not in the highest principal energy level as they fill. So as review, let's go ahead and do a couple of electron configurations. This should be a familiar skill from last year. We'll go ahead and start by having a look at bromine, which is element number 35 on your periodic table. Now, two different ways of doing this. The first, if you have a look to the right there, is to use the Aufbau diagram, which we provided you last year as a tool to use on your tests. Unfortunately for you, you will not get this Aufbau diagram, obviously, on the AP test, but let's just use it as a review anyways. We need to count up 35 electrons using this Aufbau process. And if you recall from our earlier discussions of the orbitals, within any given s orbital, you can hold a total of 2 electrons. A p orbital can hold a total of 6, a d can hold 10, and an f orbital at a given energy level can hold 14 electrons. Which means I just need to start with the lowest potential energy level electrons in that 1s orbital and simply count up, filling them according to the Aufbau process until I get to a total of 35 electrons. And you can see that I would do that by using the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then watch carefully here as we kind of go into this zigzagging diagonal pattern now, going from 4s back up to 3d10, which is a total of now 30 electrons, meaning that to get up to bromine's total we need of 35, we would require a total of 5 electrons in that 4p orbital. So again, our electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now that was again using that Aufbau diagram. A much easier way of doing this, if you have a periodic table, which you will have available to you on the AP test, is to recognize again that the shape of the periodic table is dictated by the electron configurations of those atoms. Recall that the group 1 and 2 on the periodic table, that's the alkali metals and alkaline earth metals, are filling s orbital electrons in the nth shell, where n is the principal quantum number. The block over on the right-hand side over here is what we refer to as the p block electrons, the p block elements, and we fill, you see there, 6 p electrons going across that block. And then in the center, those transition metals, again, are the 10d orbital electrons filling as we go across that block, with the actinides and lanthanides, our inner transition metals down at the bottom, representing the f orbital electrons. So following the periodic table, easier than the Aufbau diagram, we can just read through it now from start to finish, starting again with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. And you see we end up with the same configuration we used with our diagram earlier. So that's bromine. Let's now have a look at the aluminum ion. Now this is not aluminum metal, this is aluminum ions. That aluminum ion is an Al3 positive ion, and recognizing that that aluminum ion has lost 3 electrons as compared to a neutral aluminum atom, we can look at the atomic number for aluminum of 13, which means that aluminum atoms, again, would have 13 electrons in their neutral state, and then subtract 3 of those electrons, recognizing that the positive 3 charge means that we have fewer negatives in our ion there, giving us a total of 10 electrons we need to fill. So again, if we have 10 electrons following our Aufbau process, that would give me a electron configuration of 1s2, 2s2, 2p6 for a total of 10 electrons. And note there, importantly, that that aluminum ion ends up with a now full outer shell in the second energy level, according to what we introduced to you last year called the octet rule, telling us that as atoms form ions, they tend to form ions in which they end up with a complete outer shell, either by gaining electrons to get a full set of 8 s and p electrons, or by losing electrons to leave their previous outer shell filled either way. So one last idea in relation to electron configurations that sometimes gets tested by the AP test is an idea we discussed last year about magnetism. we recognize that because these electrons are moving charged particles and moving charges generate magnetic fields, atoms can exhibit magnetic characteristics. There are two possible magnetic characteristics these atoms will manifest based upon the atom's electron's configuration. Those are what we refer to as paramagnetism and diamagnetism. So, to review from last year, atoms are referred to as paramagnetic if they have any orbitals which are occupied by unpaired electrons. If you kind of think about atoms with their electrons being paired off in those orbitals, one spin up and one spin down, because the spins are opposite for those electrons, the orientation of the magnetic field generated by those electrons is opposite if their spins are opposite. And so the opposite spins kind of cancel out. But in the event that there is an atom with an orbital which is occupied by a single electron without a pair, that single lone electron generates a magnetic dipole moment, which is not canceled out by an oppositely spinning electron, and therefore that atom acts like a little tiny magnet. It is attracted into magnetic fields. The opposite condition of paramagnetism is atoms that are referred to as diamagnetic. A diamagnetic atom is an atom in which all of the orbitals are completely filled with electron pairs. That is to say that there are no unpaired electrons present in the electron configuration for the atom. The condition of being diamagnetic actually causes, to a small degree, atoms to be repelled by external magnetic fields. And diamagnetism also happens in atoms which have unpaired electrons, that is, where all those paired electrons exist. There is dimagnetism present as well, but paramagnetism is dominant over dimagnetism. And the more unpaired electrons there are present in the atom, the more paramagnetic the behavior of that atom is overall. Now, as an interesting side note, a video we showed you last year, because in molecular compounds, the electrons pair off when atoms form bonds with one another, we find ourselves in a situation that molecular compounds, for the most part, exhibit diamagnetism. And that implies if you place something made up almost entirely of molecular compounds rather than atomic species, like, say, a living thing like a frog, into a very, very powerful magnetic field, the diamagnetic properties of those molecules cause the object to essentially be repelled by that magnetic field, and you can do things like levitate very, very small objects like our poor unfortunate frog here that we showed you in the video last year. So to finish up this lecture, let's just work a couple of last examples here, putting together a couple of ideas. In this example, we're going to go ahead and give the quantum numbers that describe the highest energy electron in each of the following species. Now remember, every single electron in these species has its own set of 4 quantum numbers. We're just focusing on the one that is the highest energy electron in this species that essentially makes it different from the elements that came before it. And in addition to the quantum numbers, we're also going to determine whether the atom of each of these species is para or diamagnetic. So the first one we're going to go ahead and do here is lead. And the first thing we need to start off with is a quick trip through the periodic table to find the electron configuration for lead. So if you look on the table here and you find lead, lead is element number 82 on the periodic table. And we're going to go ahead and use the noble gas shortcut we introduced to you last year for the electron configuration for lead. So if we look back before element number 82, the previous noble gas is xenon, Xe, element number 54. So we'll start with the electron configuration for xenon, put that in brackets, and then follow along from there on the periodic table to count up to lead. We end up with xenon, followed by 6s2, 4f14, 5d10, 6p2. So there's our electron configuration, and let's go ahead and circle there the highest energy electron. That's the last filled electron in that lead atom, is that 6p2 electron. So let's go ahead now and give the quantum numbers that describe that 6p2 electron. We are looking for the 4 quantum numbers n, l, m sub l, and s. We'll start off with n. This is an easy one. The principal quantum number, the shell number of that highest energy electron, the 6p electron, is 6. That is, we're in the sixth shell. So we've got the principal quantum number of 6. For L, the shape quantum number, recall that we gave you values of L which correlate to the s, p, d, and f orbitals of 0, 1, 2, and 3. So for a p electron, our azimuthal quantum number L is 1. And here's where a little bit of remembering from last year will be useful in order to determine the orientation in space of the p orbital we're dealing with here. Recall the allowed values for the magnetic quantum number go from minus L to positive L. And in this case, L is 1, which means the orientations in space for the px, py, and pz orbitals are -1, 0, and +1, respectively. And we're just going to go ahead and count up to the number of orbital that we're dealing with here. First off, going spin up, which would be -1 followed by 0 for that second electron. So our orientation in space quantum number here, the magnetic quantum number for lead, the highest energy electron, is a 0. And last but not least, for the spin quantum number, recall that the spin quantum number can either be a -1/2 for spin up or a +1/2 for spin down. Because this is the first electron in that orbital, we call that one spin up, and that gives us a value for the spin quantum number of -1/2. Now, we've got our 4 quantum numbers. The second part of our question was to determine if the atom of lead is going to exhibit para or diamagnetism. And it might be tempting to think, well, this is going to be diamagnetic because it ends in an even number of electrons. But remember, Hund's rule tells us that the electrons will always occupy an unoccupied suborbital at a given energy level before they pair off. Which means if we're looking at that 6p orbital, all of the previous orbitals up until that point, yeah, they're filled, and therefore would be diamagnetic, but that 6p orbital is occupied by 2 electrons, which fill suborbitals, both in the up spin position. So we've got 2 unpaired electrons present in that lead atom, which implies, therefore, atoms of lead would be paramagnetic. So that's our first example. Let's go ahead and have a look at the second example, which is magnesium. A little bit easier for our electron configuration. We're now looking at element number 12, so we need to use our Aufbau principle to get up to 12 electrons. And again, following along in the periodic table, we'll go ahead and start off with the electron configuration 1s2, 2s2, 2p6, 3s2. So we've got our electron configuration, and you see there that our highest energy electron is that second 3s electron. So we can now give the 4 quantum numbers n, l, m sub l, and s for that 3s2 electron. Fairly friendly at this point. We are in the third shell, so our principal quantum number is 3. We are filling an s orbital, and recall the azimuthal quantum number for an s orbital is 0. And happily for us, we've got some easy orientation in space to deal with here because a sphere can only be oriented one way. There's only one possible magnetic quantum number, m sub l, for this particular electron, which is going to be a 0 as well. And if you note here that we are filling the second electron in that s orbital, that implies that that electron is being filled spin down, which gives us a spin of +1/2. And we've got our 4 quantum numbers. Last but not least, all we have to do is determine if this thing is para or diamagnetic. And if you have a look there in the electron configuration, you'll see that all of the orbitals, including that valence shell of our 3s orbital there, is filled completely, which implies, therefore, all of the electrons are paired off, and therefore magnesium atoms themselves would exhibit diamagnetic characteristics. And that's it for this lecture. Thanks for watching.